Good morning, students. So welcome to another lecture of control systems. And in today's class, we are going to see about force voltage and force current analogy. So in the previous lecture, we have seen what is the representation for force, mass, dashpot, and spring in terms of force voltage and force current equivalent. So the conversion table is shown here for your reference, and we are going to be using this conversion table into solving problems or numericals where you are required to represent or draw the electrical circuit diagram for a given mechanical system. Good. So let's get started. So we will do few sums today, few numericals, and it is best if you know this conversion table, since in exam it will be not given as part of your question. So the numerical for today is something like this. So we have three masses M1, M2 and M3, which are connected with your spring and dashboard. So we have seen multiple questions like this previously. So there's another typical question from your mechanical system, but the question is asking us to draw the electrical equivalent. So the problem solving here for this mechanical system is in terms of your electrical equivalent, and we will be doing that in the same steps, same rule set we have followed for your mechanical system. So what was those rule sets? So just a quick recap into these rule sets. You have to isolate masses separately. So we have three masses M1, M2 and M3. You need to isolate these masses, and after you isolate these masses, you need to look for the relative displacements, the displacements of the mechanical components between two masses, and that would be your relative displacement. And finally, you need to write your force equation using all these things. So the first thing we are having here is your mechanical equivalent differential model, but what is the relative displacement? So the relative displacement is my K3 and K4. So if you take a closer look, you can see that your K3 is between masses M1 and M2, and your K4 is between M2 and M3. So keeping that in mind, so I am going to write the differential representation for mass M1, M2 and M3, and then I'm going to convert that differential representation into my electrical representation. So the previous lecture we saw, we took the differential representation, we converted it into Laplace representation, right? And that Laplace transform representation helped us in obtaining the transfer function. So in this case, what we are doing is we are going to use the differential representation to derive the electrical representation or the voltage representation in the first case and your current representation in the second case. And from those electrical representation, we are going to draw the circuit diagram, and that is your question for today. So these things are very crucial, like I told you, in systems where we need to control a mechanical moving part with the help of a voltage or a current. This could come in handy in designing those systems. So the differential equation is given, and I'm not telling much on the rules. I can tell you can tell by seeing the relative displacement is for K3, which is x1 minus x2. X1 is for the mass M1 in question. So my force to mass and force to voltage is shown here. And now the electrical equivalent is what I'm writing now. You can see for my mass M1, my electrical equivalent is L1, B1, it's R1, and for K1 it's 1 by C1. So that is the force to voltage conversion we have for the differential equation shown in 3, right? The 4 gives your voltage or your electrical differential equation. Good. So now we are ready to draw the circuit diagram for this mass M1. So how does your circuit diagram translates to or maps to from your differential equation? So what we need to do, the rule set that we need to follow here is the series parallel, right? So we need to identify which are the things that are going to be in series. So all will be in series, all the components will be in series which are not having a relative displacement term attached to it. So which means in our case for M1 only K3 is the spring which is having a mechanical a relative displacement, and that is the only component which in my voltage circuit diagram it's gonna appear in parallel. Rest of the things K2 B K1 B1 and my M1, right, which translates to L R and C, L1 R1 and C1, they come in series. So now my C3 is in parallel here because that is having a relative displacement component. So that is the rule set you need to remember when you need to draw the force voltage equivalent circuit. So do not get confused, do not mistake between the force voltage and the force current, which will be seen next. So for the mass M2, for the isolated mass M2, we are having the following. So we are going to again do the same thing, and for my mass M2 my relative displacement comes in two, right, two springs K3 and K4 if you look at the question. So now which means I can easily tell my force voltage equivalent for mass M2 is going to have my K3 and K4 in parallel, whereas my K1, B1, K2, sorry, the K2, B2 and my M2, they are going to be in series. So my K2, B2 and M2 will translate to L2, R2 and C2. So that will be in series, and the relative displacement component of my K3 and K4 translates to C3 and C4, which is going to be in parallel. Good. So that is the force voltage for my mass M2. Now you can easily identify when I draw this circuit that the C3 is common in both, right? C3 is between M1 and M2, and even in your electric circuit diagram, because the K3 is between M1 and M2, so your C3 is also going to be connecting the M1 circuit, equivalent circuit in voltage, and your M2 equivalent circuit in voltage. So for now we'll draw this as my M2 circuit diagram. I have my L2, C2 and R2, and my C3 and C4 are in parallel. Okay, good. So I just want you to see where these positions come. So my C3 obviously should come on the left hand side, and my C4 on the right hand side, because their equivalent of K3 and K4 is appearing on the left and right in the given question. Good. So that is my force voltage equivalent for my mass M2. Moving on to mass M3, what do we have? We have a much simpler component here. We have in K4, which is a relative component, and that is pretty much it. So we have your K4 force and your force due to the mass M3 itself, which is Fm3, and that is your differential representation for M3. Now converting this to an force voltage representation, my M3 will be my L3 and my K4 will convert to C4. And here my relative displacement is with K4, so which means the K4 is going to be in parallel, whereas my C4 is going to be in, right. So my mass M3 is going to be in series. Good. So you have your series and parallel, And that is what we are drawing here. My L3 is in series and my C4 is in parallel. Now you need to do an equivalent circuit for the entire system, which means for mass M1, M2 and M3, whatever you have done separately till now, you are going to bring all those together and have a single equivalent circuit. And we are in the while doing this, what we need to check is you need to look for the connecting link. So whenever you see this, you can see that your C3 is the connecting link between 1 and 2, and your C4 is the connecting link between 2 and 3. So now bringing these together, bringing 1 and 2 and 3 together, you are going to get your equivalent circuit as shown in this figure. Now let's look at the force current equivalent. So your force current equivalent is given here as what? So you are going to do the same things, and we are going to combine. We are going to get three circuits for my M1, M2 and M3, and then we are going to draw the equivalent circuit for the entire system. So the procedures are going to be the same steps have to be followed. So we move on directly to writing the differential representation for masses M1, M2 and M3. So here the conversion is going to be the force to current conversion. So which means my mass translates to capacitance, and my B translates to resistance, and my K translates to inductance. Good. And with this current equivalent, I can draw my equivalent circuit. And the rule set that we are going to follow for your force current model is all in parallel. So which means all the components are in parallel unless they are a relative displacement component. So this is what it means for a force current equivalent circuit. So your all the components are in parallel except your relative displacement component, which is L3. Good. So now for the second equation, you can now definitely you can predict how your equivalent circuit in force current analogy will be. So you will be having C2, L2 and R2 in parallel, and your L3 and your L4 in series. Good, because that is the equation we are having. So drawing that equation's equivalent diagram, I'm going to have my L3 and L4 in series and my C2, R2 and L2 in parallel. Good. Similarly, we can do for my mass M3. So for M3, what we are gonna do, so we have a relative displacement there also. So that is going to be in series, and the other thing is going to be parallel. So it's going to be just the vice versa case as what we saw in your force voltage. So which means your C3 this plus 1 by L4. So here your L4 in series and your C3 is going to be in parallel. So that is your equivalent circuit. Good. So now we have 1, 2 and 3. We will join these two with the common link. So here the common link is your series inductance L3 and L4. So using these series inductance, we will be able to join these three circuits for masses M1, M2 and M3. And that is going to give you the overall circuit diagram or the overall force current equivalent circuit diagrams for the entire system. Good. So this is how you solve these questions in your exam. Hope that clears this topic. I'll see you next week with more on control systems. Thank you.